So today we will discuss AC fundamentals, how we can generate the alternating quantity, either it is voltage or current. We know Faraday's laws of electromagnetic induction. So Faraday's law of electromagnetic induction, it states two laws. First law states that whenever a conductor cuts the magnetic field, an EMF is induced in it. Okay. The second law states that the induced EMF is equal to the rate of change of flux linkages. Right? So to generate an EMF, what we require? The requirements to generate current or voltage. So Faraday's law says that whenever a conductor cuts the magnetic field, it induces an EMF. So we require magnetic field first one magnetic field and the second one is conductor. Okay. So if we have the magnetic field, so let me draw a magnet, a bar of magnet. So this is south pole and north pole, and another bar of magnet. So this is south pole and north pole. So the flux will flow from north pole to south pole, the magnetic field. That's the flux. Okay. So as the south pole has not much influence with this flux, we can neglect the south pole, and here the north pole will not have much interaction with this flux, so we can also neglect this north pole. So now we know the flux will flow from north pole to south pole. So let we place a conductor in the magnetic field. So there is a conductor in the magnetic field. Okay. Now if the conductor is stationary, the flux will not have any changes on the conductor. So there is the induced EMF in the conductor is 0. Okay. So there is no rate of change of flux is 0. There is no d by dt, right? So induced EMF is 0. Okay. So to get induced EMF, we have to change the flux. Okay. So for that reason, what we have to have motion of the conductor. Okay. So we have to move the conductor in this magnetic field in such a way that the conductor cuts the magnetic field. So an EMF will induce in the conductor, right? So the third one is the motion of the conductor. Okay. So now once the EMF induced in the conductor, so we can determine the direction of the induced EMF by using Fleming's right hand rule. Okay. So let's take your fingers, forefinger, thumb finger and middle finger. So you have to keep in such a way that every finger is make right angle to each other. So here the forefinger indicates the magnetic field, direction of magnetic field, and the middle finger indicates direction of induced EMF. The thumb indicates the direction of the motion, conductor motion of the conductor. Okay. So let us take a single turn coil. So single turn AC generator. So north pole, south pole. So flux is flowing from north pole to south pole. So we placed a single turn coil in the middle of the flux. Okay. And the single turn coil ends are connected to the slip rings. So these two rings are called slip rings. These rings are soldered to the coil ends. And the slip rings make contact with the brushes. The brushes are fixed and the brushes are connected to the load. The load will receive the current from the single turn coil. Okay. Now to make current flow through load, we have a conductor now and we place the conductor in the magnetic field. So what we have to do now? We have to move the coil. That is called third one. So motion of the conductor. So when you rotate the coil, single turn coil, so there is a d phi by dt and an EMF will induce in the conductor, and that EMF which is induced in the conductor will flow to the slip rings through the brushes, and this is the load resistance, and it will consume the energy and it will circuit close. Okay. So this is the galvanometer to measure the deflection of the induced EMF. Okay. So let me draw a circle. So here the coil the coil will move in a circular direction. So now this is the conductor which is in the bottom of the coil. So let me draw another conductor. So this is the conductor at the top of the coil. Right. So this is the bottom conductor and this is top conductor. Okay. Here if you draw axis, okay. So let us assume the coil is rotating in clockwise direction. Okay. And the coil is rotating in clockwise direction. Here the effect of magnetic flux on this axis is minimum. The effect of magnetic flux at this axis is minimum. So the EMF induced at this point is 0. Okay. As the coil moves, this conductor cuts the magnetic field under the influence of north pole from downwards to upwards. Okay. And the top conductor cuts the magnetic field which is in the influence of south pole. So this top conductor, when it will rotate from upwards to downwards, it is in the influence of south pole. So that direction of the motion is different for top conductor and it is opposite to the bottom conductor. So it is the bottom conductor is cutting the magnetic field from downwards to upwards. And the top conductor is cutting the magnetic field from upwards to downwards, right? So the EMF induced in the conductor which is in the bottom is opposite to that of the top conductor. Okay. So let me draw another diagram. So this is the north pole, south pole, so magnetic flux. Let us consider the coil rotates 90 degrees. So when it rotates 90 degrees, the conductor which is in top position, that will be here, and this is the conductor which is in bottom. Okay. So now the coil make a 90 degrees rotation. Now the effect of magnetic field on this conductor is maximum now. The effect of magnetic field on this conductor is maximum now. So this is the omega t, and if you draw the induced EMF which is induced in the conductor, so it is E max. Okay. And this is 0. So 0 means the conductor, the coil which is on the axis. So at this position, the effect of magnetic field on the conductor is 0. So the induced EMF is also 0. Okay. So when the bottom conductor is cutting the magnetic field from downwards to upwards, okay. So the effect of magnetic field gradually increases. So as the effect is increasing, the EMF, amount of EMF induced in the conductor is increases. Okay. So since E is equal to N d phi by dt. Okay. So the magnitude of EMF depends upon the number of turns, and it also depends on the magnitude of the flux, rate of change of fluxes, d phi by dt, and the magnitude of flux. Okay. In this case, as this conductor is cutting the magnetic flux from here to here, the magnetic flux strength will increases. Okay. As the strength increases, the amount of induced EMF in the conductor increases. Okay. So this is the Emax. So the maximum EMF is induced at this position. So now the coil is at right angles to the magnetic field. At this condition, the maximum flux, the effect is maximum on the conductor at that position. Okay. Now let us consider, let me draw another diagram. North pole, south pole. Okay. So this is a circle. The coil will move there along the circle. So if it rotates another 90 degrees, the coil rotates another 90 degrees. This conductor cuts the magnetic field from here to here, and it will come to here, and this conductor comes to there. So this is the conductor. Now it is in top position, and this is now it is bottom conductor. Okay. Right. So now here, when the conductor is cutting the magnetic flux from this position to this position, the effect of magnetic flux on the conductor decreases gradually. Okay. As the effect of magnetic flux on conductor decreases gradually, the amount of induced EMF in the conductor also decreases gradually. And at this position, there is no effect of the magnetic field. So this is magnetic flux. So at this position, the coil, when it is on parallel to the flux, the effect of flux on this conductor is 0. Okay. So the amount of induced EMF is 0. Okay. So as the conductor moves from this position to this position, as the effect of flux on conductor decreases, the amount of induced EMF also decreases gradually, and it comes to 0. Okay. So this is 0, and this is 90 degrees, and this is at 180 degrees. Okay. If we move the coil further, let me draw another diagram. So this is south pole. So let me draw flux also. Flux. So let me draw a circle. Now the coil completes 50% of the circle, half portion of the circle. Okay. Now the conductor here, when it is under influence of the north pole, this conductor cuts the magnetic field from downwards to upwards, right? So now when the conductor is it is in the south pole, when it is rotating further 90 degrees, now it will come under south pole. Okay. So up to from 0 to 180 degrees, this conductor is under the influence of north pole. When this conductor is under influence of the north pole, it is cutting the magnetic flux from downwards to upwards. Okay. When this conductor cuts the magnetic field from upwards to downwards, so when it is under south pole influence. Okay. When it is under south pole influence, the direction of conductor is changes. Okay. So the amount of induced EMF direction also changes in the conductor. Okay. So I repeat the point. Here, this conductor from 0 to 180 degrees, it is under the influence of north pole, and when it is under the influence of north pole, the conductor cuts the magnetic field from downward direction to upward direction. Okay. Now when it is under south pole influence, this conductor cuts the magnetic field from upwards to downwards. So from 180 degrees to 360 degrees, the direction of the motion is changes. When the direction of the motion changes, according to Faraday's Fleming's left hand or right hand rule, when the direction changes, the amount of induced EMF also changes. So it will reverse. Okay. So now take this is at 90 degrees and this is at 180 degrees. Right? So let after 90 degrees, so that means at 270 degrees, the coil, this conductor will be here, perpendicular to the magnetic field, and the other conductor, now it is, earlier it is under south pole influence, now it is under north pole influence. So this conductor, earlier it is under south pole influence and it is cutting the magnetic field from upwards to downwards. Okay. And now it is under now south pole influence. When it is under south pole influence, the conductor will cut the magnetic field from downwards to upwards. So here also the amount of induced EMF direction is changing, has changed. So here let me take a point, here it is at 270 degrees. So now as the direction of motion changes, the direction of induced EMF also changes. So it is positive direction and this is negative direction. Okay. So here as I told you, at this point the effect of magnetic flux on conductor is 0. So the amount of induced EMF is 0. The amount of induced EMF in the conductor is 0. When the conductor is cutting the magnetic flux from this position to this position, the effect of magnetic flux increases gradually and it will reach its maximum when the conductor is perpendicular to the magnetic field. Okay. And this is 0 and it is increasing gradually, and at 270 degrees, when the conductor is perpendicular to the magnetic field, the amount of induced EMF is maximum and this is minus Emax. Since the direction of the motion of the conductor is changing. Okay. So it is minus Emax. So let me draw another diagram. So for 360 degrees. So north pole, south pole. So magnetic flux from north pole to south pole. So when is at 270 degrees, this conductor is perpendicular and under the influence of south pole, and then it will move from 270 degrees to 360 degrees. So it will cut the conductor from upwards to downwards and the effect of magnetic field decreases. Okay. The effect of magnetic field decreases from maximum to minimum as it reaches to 360 degrees. Okay. So here it is minus Emax. When the conductor is rotating from 270 degrees to 360 degrees, the effect of the direction is same. Okay. Here from 180 degrees to 270 degrees, it is cutting the magnetic flux from upwards to downwards. The direction is same. Okay. So from here to here, the effect of flux is increases on the conductor. From 270 degrees to 360 degrees, the effect of flux on conductor decreases gradually. And hence, the induced EMF in the conductor also decreases gradually and it becomes 0 at 360 degrees. Okay. And this is the conductor positions at 360 degrees. Okay. So earlier the first position we came now. So if we move further the coil, so now it is we complete one revolution. So from 0 to 360 degrees. So from 0 to 90 degrees, the effect of flux on conductor is increases, and as it is increases, the amount of EMF induced in the conductor increases. So it is increases to E max, from 0 to E max. So it is from 0 to 90 degrees. So it is cutting from downwards to upwards, and the effect of magnetic flux increases on conductor when it is under influence of north pole, and when it is moving towards the perpendicular to the magnetic flux, the effect of magnetic flux increases. So at 90 degrees we will get the maximum EMF E max. So from 90 degrees to 270 degrees, so the direction is same. It is cutting, the conductor is cutting from downwards to upwards, but the effect of magnetic flux decreases gradually, and at this position, this one, right? So at this position, the effect of magnetic flux on conductor is 0. So this is from E max to 0 here. Okay. So now from 180 degrees to 270 degrees, what happened? So the conductor which is under north pole, now it is coming under south pole, and now it is cutting the conductor from upwards to downwards. Earlier it is cutting the magnetic field from downwards to upwards. Now when it is under south pole, it is cutting the magnetic flux from southward to from upwards to downwards, right? So when it is under south pole, the direction, the motion of the conductor changes. When the motion of the conductor changes, according to Faraday's law of Fleming's left-hand rule, the direction of induced EMF changes. Now it is from negative. Now it is negative. So as the effect of magnetic field increases from 90 degrees to 180 degrees, so it is increases from 0 to minus E max. So from 180 degrees to 270 degrees, as the motion of the conductor not changes, but the effect of magnetic field decreases from maximum to minimum. So it is minus E max to 0. So this is for one revolution. Okay. So if you further move the coil continuously, you will get another waveform. So like this it continues. Okay. So let me show the diagram at different positions. Okay. So now the position A is at 0 degrees. When it is 0 degrees, the effect of magnetic flux on the conductors is 0. So the induced EMF is 0 now. So this is the point at A. Okay. So now when it is at 90 degrees position, so it is the coil is perpendicular to the magnetic field. So when it is perpendicular to the magnetic field, the effect of magnetic flux on the conductor is maximum. So here we got the maximum induced EMF at B position. At C position, now this is at 180 degrees. The effect of magnetic flux on conductor is minimum. So here we got the 0. Induced EMF is 0. And at 270 degrees, the motion of the conductor changes. So the direction of the induced EMF changes, and now it is perpendicular. Since it is perpendicular to the magnetic field, so the effect of magnetic flux is maximum at this position. So it is minus E max. So at 360 degrees, the effect of magnetic flux on conductor is 0. So the EMF is 0. Okay. Any queries? So this is when we consider only coil. So now when it is in parallel with the flux, the induced EMF is 0. When the coil is perpendicular to the flux, the induced EMF is maximum. And there is at second position it is 90 degrees, third position it is 180 degrees, and fourth position is at 270 degrees, fifth position is at 360 degrees, as we discussed earlier. So now we will derive the EMF equation. So we know according to Faraday's laws of electromagnetic induction, E is equal to minus N d phi by dt, right? So the flux is not constant at all the places. So it depends upon the position of the conductor. Okay. So as here the coil is rotating in anti-clockwise direction with the speed of omega, where omega is the angular velocity in radian per second. Okay. And after some time, So the coil makes an angle, theta angle. So this is the coil axis, and this is the axis which is perpendicular to the coil, orthogonal. So after some time the coil makes an angle theta, so where theta is equal to omega t, and at this position the flux is maximum. So to get the flux at that point, so what is the flux at that point? So that is phi is equal to phi m cos omega t or cos theta. Okay. So let me make it more clear. This is flux direction, and when it is in perpendicular to the coil, the flux is maximum at this position. Okay. And this is the coil. And the coil here makes the angle theta with x-axis. The theta is equal to omega t, where omega is the angular velocity. As the coil rotates anti-clockwise with the speed of omega. So omega is the angular velocity in radian per second. Okay. And here if you take the axis orthogonal to the coil, and here this will makes the angle theta, this axis, and this magnitude with respect to this one is can calculate by using cos theta, phi max cos theta, this component, phi max cos theta. So the flux on the conductor at this position is phi max cos theta. So by using that formula we can calculate or we can determine the flux at any time by using phi is equal to phi max cos theta. Okay. If the coil is at perpendicular to the magnetic flux, theta is equal to 90 degrees. Okay. Theta is equal to 90 degrees when it is parallel to the flux. Then we get the flux is maximum. Okay. So if we consider, we know that according to Faraday's laws of electromagnetic induction, E is equal to minus n d phi by dt. Okay. Here we know that phi is equal to, at any instant, phi is equal to phi max cos theta at any instant. So let's take this is equation 1 and this is equation 2. Now let's put the equation 1 in equation 2, then you will get the E is equal to induced EMF in the conductor minus n d by dt. So phi is now phi m cos theta. Okay. Here the derivative is with respect to time. Here we have to change the theta into omega t. So theta is equal to omega t. So if you replace the theta with omega t minus n, so phi m is the constant, we can take it out. So minus n into phi. Now it is d by dt cos omega t. Okay. Now if you apply the derivative, now it is minus n phi m. So it is omega t. So it is omega into minus sin omega t. Okay. So since it is cos omega t, the derivative of cos omega t is omega minus sin omega t. Okay. So now it will become omega n phi m sin omega t. So E is equal to. Okay. So at which value the induced EMF is maximum? When sin omega t is equal to unity. When sin omega t is equal to 1, you will get the E is maximum. Okay. So induced EMF E is maximum at sin omega t is equal to 1. Okay. So that means E max is equal to omega n phi m. Okay. Now this omega n phi m is nothing but E max. We can replace this omega n phi m with E max. So now the induced EMF E is equal to E max sin omega t. So this is the induced EMF at any instant in the conductor or coil. Okay. E is equal to E max sin omega t. So since if we plot the induced, if they plot all the induced EMF at all the points, okay, we will get the plot sine wave. Okay, sine wave. So the amount of induced EMF is proportional to the sine function. We are calling the waveform it is sine wave. Okay. So if you draw the induced EMF here, so sine 0 0 from sine 90 you will get maximum EMF here. This is Vmax, and here it is at 180 degrees, and here at 90 degrees 0. So let me draw it more clear. So this is 360 degrees, and this is 270 degrees. Okay. So here this is E max, this is minus E max. Okay. So E is equal to, we can calculate the induced EMF at any instant. E is equal to E max sin omega t. Okay. So if omega t is nothing but, if omega t is equal to 90 degrees, sin 90 is equal to 1, right? So you will get the value induced EMF is maximum. Okay. So if omega t is equal to 270 degrees, so what is the value? Sin 270 minus 1. So you will get negative maximum. Okay. So here induced EMF is equal to E max sin omega t, which is equal to E max into sin theta. So here the waveform is there, it is not visible properly. So here we have to define how important is the technology. So let me draw the waveform more clear once again. So this is omega t, E, this is E max, this is minus E max. Okay. Let me, the first definition is instantaneous value. So the instantaneous value is the value of an alternating quantity at any instant is called instantaneous value. Okay. So if we take the value at this instant, so this is E, this E is the value at this instant, this is called instantaneous value. Okay. The instantaneous value is the value of an alternating quantity at any instant, it is called instantaneous value. And the next one is cycle. Cycle is one complete set of positive and negative values of an alternating quantity is known as cycle. Okay. So here from 0 to 180 degrees we will get the values, positive values of alternating quantity. From 180 degrees to 360 degrees we will get negative values of alternating quantity. So if you take one complete set of all positive of alternating quantities and values of alternating quantity and all negative values of alternating quantity if you take, so this will make a cycle. Okay. Cycle is nothing but one complete set of positive and negative values of an alternating quantity. The next one is alternation. Alternation is nothing but one off cycle of an alternating quantity is called an alternation. This may be a positive off cycle or negative off cycle. Okay. So from 0 to 90 degrees, this is called one alternation which is positive. Okay. Or from 180 degrees to 360 degrees, this is another alternation, but it is negative. Okay. So one off cycle of an alternating quantity is called an alternation. Alternation may be a positive one or negative one. Okay. So if it is from 0 to 180 degrees, it is positive value. From 180 degrees to 90 degrees, it is negative. The time period. So time period is the time taken of the alternating quantity to complete one cycle is called the time period. So time period is indicated with capital letter T. Okay. So it is the time taken of the alternating quantity to complete one cycle. So this is the time, how much time it will take to complete one cycle, that is one positive half cycle and one negative half cycle. So this is time period T, so which is indicated with the letter T. The next definition is frequency. So frequency, the number of cycles that occur in 1 second is called the frequency. The number of cycles occur in 1 second is called frequency. Frequency indicated with letter f, small f. Okay. And unit is number of cycles per second. You can easily determine the frequency is nothing but the number of cycles per second. The unit of frequency is Hz. Frequency is nothing but the reciprocal of time period 1 by T, or T is equal to, we can tell T is equal to 1 by F. Where time period is the time taken to the alternating quantity to complete one cycle. Frequency is the number of cycles that occur in a second. The next one is amplitude. Amplitude is the maximum value of either it is positive or negative of an alternating quantity. It is called amplitude. So this is the maximum value. So this is called amplitude. So the amplitude may be a positive or negative value. So the maximum value of an alternating quantity, either positive or negative. So this is positive amplitude and this is negative amplitude. So for positive amplitude it is Emax, the value is Emax. For negative amplitude the value is minus Emax. Okay. Phase difference. Phase we can define as it is the fractional part of time period or cycle through which the quantity has advanced from the selected zero position of reference. Okay. So I can explain you this more clear with an example. If we want to know the time now, so we may say it is 10 or 10:30. Okay. So that 10 is what is 10? So from we have to have a reference. So from reference, the reference is where the day is changed. So from where at the point when the day is changed. So at the midnight, the date will change at 0 hours, right? So from 0 hours, we are counting the time, 1 hour, 2 hour, 3 hour, up to here it is 10:30. Okay. So the reference is 0 hours. Okay. Here, in the same way, here the reference is 0. Here the reference is 0. At any instant, the value of the alternating quantity at any instant is nothing but phase. Okay. So let me take at the phase of 5 by 2 or 90 degrees. At the phase of 90 degrees, the value of the alternating quantity is Emax. Okay. So that 90 degrees is the phase. Okay. So the maximum value is, you will get the alternating quantity at the phase of 90 degrees. Okay. So it will get the negative maximum at the phase of 270 degrees. Okay. So phase is nothing but the fractional part of time period or cycle through which the quantity has advanced from the selected zero position or reference. So the next one is phase difference. Phase difference, when two alternating quantities of same frequency have different zero points, they are said to have a phase difference. So let us have two alternating quantities like A and B. The condition is the frequency of A and B should be same. What is frequency? The number of cycles occurred in 1 second is nothing but frequency. Okay. The frequency of, if you want to compare the phase difference between two alternating quantities, their frequency should be same. Okay. Let us take the alternating quantity A. We started at A, and the alternating quantity B started at 60 degrees. Now the phase difference between alternating quantity A and B is, now it is 60 degrees. So 60 minus 0, 60 degrees. So this is the phase difference. Okay. Now if we go to the definition, so when two alternating quantities of same frequency have different 0 points, so here the alternating quantity A is the point is 0 point, and the alternating quantity B started at 60 degrees. So it has two different 0 points. They are said to have a phase difference. So here the phase difference is 60 degrees. Here we can say that A leads the B with an angle 60 degrees, since A started earlier than B. Okay. So or you can tell that B lags behind A with 60 degrees. Okay. The phase difference is 60 degrees. So I think is it visible, the diagram? So which is in thick color, that is A, so which is in light color, that is B. Here the phase difference between A and B quantities is 90 degrees, and here A is ahead of B, or we can tell that A leads B with an angle 90 degrees. So in the first figure. So this is the waveform of B. Okay. So B starts here. So the difference between A and B is 90 degrees. Okay. A started earlier than B. Okay. So that means we can tell A leads B with an angle 90 degrees. The phase difference of A and B is 90 degrees. And here B started first at 0 and A started after 90 degrees. So here we can say that the phase shift is 90 degrees. The phase shift is same. B is now ahead of A and B leads A now. Okay. So this is the phase representation of an alternating quantity, phase representation. So as the coil moves in a circular direction, if we take the circular motion, so if we take this OA is the magnitude of maximum magnitude. OA is the maximum magnitude. So this is of alternating quantity. Okay. So when we will get the phasor here from 0 to B, so if you draw a line from here to here, the magnitude is 0 here. The magnitude is 0 here. So when the coil is made at an angle theta here, okay. So even the magnitude of phasor is 0 to O to A. Here if we draw a line to here, to the y-axis, so this is the magnitude when the coil is making at an angle theta. Okay. So but the magnitude is increases from 0 to some value, and to calculate this value, here you can take the line here. So you can take this is B. So this is the magnitude of B. Magnitude of B. So the magnitude of E, this at instant is nothing but the magnitude of OB. So as we draw a circle, if we draw a line, horizontal line from this point to here, so the magnitude of OB at this point is B. OB is equal to the magnitude of instantaneous value which are occurring here at this point. So and this theta is the phase of theta. Here 0 to theta. So this is phase of the alternating quantity at this instant. So let me draw a circle here to make you a better understand. This is OA, and when it is making angle theta, the phasor is now it is rotating in anti-clockwise direction. So when it is in zero position, the magnitude of EMF is zero. So when it makes the angle theta with the x-axis, this is the phase is now phase of the alternating quantity is theta. At this position, the magnitude of the instantaneous value E is nothing but it is equal to the magnitude of OB. So this is B. Okay. So let us take E is equal to, so the formula for instantaneous value E is equal to E max sin omega t. E is equal to E max sin omega t or theta. Okay. So here E max is nothing but the magnitude of OA. E max is nothing but magnitude of OA. When this phase are making an angle with x-axis theta, the magnitude of instantaneous value E is nothing but OB. Okay. Now OB is equal to the instantaneous value OB is equal to OA. OA is nothing but the E max into sin theta. OB is equal to OA into sin theta. So if we take the theta value 90 degrees, when we take theta value 90 degrees, here at this position OA is equal to OB. So if we take a projection at that point, OA you will get OB. So here OB is equal to OA into theta value is 90 degrees, right? So sin 90 you will get 1. So you will get OB is equal to OA when theta is equal to 90 degrees. Okay. So at this position, now here we take a projection here from here to B. Now the magnitude of instantaneous value of E is nothing but the magnitude of OB, here OB. Okay. As the theta further increases to here, as the magnitude of OB increases to here, and the instantaneous value also increases somewhere here. Okay. So this is nothing but phasor representation of an alternating quantity. Okay. Any queries? So these are the references, these are the textbooks which I referred for this topic. Principles of Electrical Engineering by V.K. Mehta, B.L. Tareja, A.K. Tareja, a textbook of electrical technology, volume 1.